Hello friends, Mr. Burrell here. We're in the end of Unit 4. We've been talking about dilations and similar triangles. We've been talking about how to know that two triangles are similar, whether it's been dilated or enlarged. So today we're going to talk about some application. So what? Now that we know all these things about similar triangles, some of these different properties, can that be used? How is that going to be helpful? So we're going to talk about some applications, some cases where we can use what we know about similar triangles to solve some problems. Before we get there, just a reminder, I showed this in a previous video, but do we remember how we would go about solving this equation? I have 3 over x equals 6 over 12. Well, I have two fractions being equal to each other, so I'm going to go ahead and cross multiply, which gives me 3 times 12, which is 36, equals 6 times x, which is 6x. Then I divide by 6 on both sides, and I get x equals 6. And indeed, 3 over 6 is equal to 6 over 12. When I reduce those fractions, they are the same. This is going to come in really handy when we're talking about solving problems with similar triangles. So by the end of this lesson, these are the things I hope that you're able to do. I want you to be able to use properties of similar triangles to solve for missing sides of similar triangles. I want you to use what you've learned about similar triangles to solve real-world problems and be able to find the scale factor for triangle similarity problems. So we're going to solve some problems. We're going to solve some things associated with these triangles. So just a little history, because I think sometimes it's beneficial to know where this stuff is coming from. So Thales of Miletus, I think that's how you say his name, was born in 624 BC. He was a Greek mathematician and philosopher. So something that he noticed, he was over in Egypt, he noticed that the shadows cast by the pyramids in Egypt were proportional to his own shadow. They were proportional to his own shadow. He was the first to introduce properties of similarity in triangles to solve for measurements they couldn't possibly get in that time. So, for example, here's, say the sun's over here, right? And Thales, my guy Thales, he noticed that this shadow on the ground, if he was like standing nearby, here's Thales, right? He noticed that his shadow, the length of his shadow, was proportional to the length of the pyramid shadow, right? So, and over here I have like the math equation that represents that Thales' height divided by his shadow was equal to the pyramid's height divided by the length of its shadow. So what he noticed is that these two triangles, the triangles formed from like the top of their heads and the top of the pyramid to the end of their shadows, those two triangles were similar triangles, meaning that the ratio of their sides, or the fractions of each of their corresponding sides, were equal to each other. So he could calculate how tall the pyramids were without actually having, take a tape measure up there to the top of the pyramids. He could figure out how tall they were using these properties of similar triangles. So that's pretty cool. So that's basically what we're going to be doing today. So if we know two triangles are similar, we can use ratios to solve for the missing sides. So for example, I have two triangles here. I have triangle ABC and triangle DEF, and I'm telling you that they are similar. Reminder that that's what this little squiggly sign means, is that those two triangles are similar. Meaning that all their corresponding angles are congruent. See this? All their corresponding angles are congruent. And their corresponding sides are proportional, meaning that the fractions of their corresponding sides are going to be equal to each other. So if I were to take like the side AB divided by the side DE, that would be equal to the side BC divided by EF, etc., etc., etc. Only problem is I don't know this side. I don't know what that side is, but I'm going to be able to find it here. So let me set up a fraction. I know AB divided by DE. AB is 6, DE is 3. So 6 divided by 3 is going to be equal to BC over EF. Or 8 over, and then EF is x. So 6 over 3 has to be equal to 8 over x. Okay, well, what can I do here? Well, as I showed on this slide, I can go ahead and cross multiply. So 6 times x is 6x. 3 times 8 is 24, so I get 6x equals 24. If I divide by 6 on both sides now, I get x equals 4. So the length of this side here is 4. And that's it. That's the end of my problem. I found that missing side is 4. Let's show some other examples. So it says the following triangles are similar. Solve for the missing sides / solve for x. So I have these two triangles right here. These two right here. And I'm saying that those two triangles are similar. Which means that the ratios of their corresponding sides are equal. Or the fractions of their corresponding sides are equal. Well, this side corresponds to this side. So 12 over 3 has to be equal to this side divided by this side. Or 20 divided by x. Well, how would I go about solving this? Let's cross multiply. 12 times x is 12x. 3 times 20 is 60. If I divide by 12 on both sides, I get x equals 5. I get x equals 5. So that's the length of this side. Now take just a second and notice how much bigger is this triangle in comparison to this triangle. What is the scale factor? How much bigger is it? Well, to get from 3 to 12, I multiply by 4. To get from 5 to 20, I multiply by 4. This triangle is 4 times as big. It has a scale factor of 4. It's been blown up by a factor of 4. Okay. Good. So, how about this triangle? I say these two triangles are similar. So I have this little triangle right here. I'm going to go ahead and redraw it out here. Boop, boop, something like that. Where this side is 4 and this side is 6. And then I have this big triangle, right, where this side is 10 and this side is z. So these two sides are going to correspond. And these two sides are going to correspond. So let's go ahead and write out the set of fractions that I would use to set up this equation. So z over 4 equals 10 over 6. I could also have written 4 over z equals 6 over 10. Notice that it doesn't matter like which way those fractions are written, I will still get the right answer. So z over 4 equals 10 over 6. I'm going to go ahead and cross multiply. 6z equals 40. If I divide by 6 on both sides, 40 divided by 6, let me check that. 40 divided by 6 is like 6.67 if I round. So that missing side right here, missing side z, is approximately 6.67. Okay. Let's do some more examples. So it says the following triangles are similar. Solve for the missing sides. So here it says triangle STU is similar to triangle LMN. See that? So I know that the ratios of their sides are going to be the same. Well, when in doubt, notice that these triangles like aren't drawn in like the same direction. So it says triangle STU is similar to triangle LMN, which means side ST are going to correspond to side LM. TU is going to correspond to MN, TU, MN. I'm just like looking in the correct order. So if I look at side ST and LM, I have 18 over 2x minus 6. And if I look at this next side, MN and TU, I have 24 over 8. Okay, so I've thrown a little bit of a wrench in the spokes because I have like 2x minus 6 here instead of just like x, you know? But I'm still going to follow the same pattern. I'm still going to do the same thing. I'm going to go ahead and cross multiply. So that's going to give me 18 times 8. I don't know that off the top of my head. 18 times 8 is 144. Equal to 24 times 2x minus 6. See that? 24 times 2x minus 6. Well, I can go ahead and distribute these. 144 equals, that's 48x minus 24 times 6 is 144. Yeah. We'll go ahead and add 144 on both sides, which gives me 288 equals 48x. And if I divide by 48 on both sides, 288 divided by 48 is going to equal x equals 6. So x equals 6. Then if I wanted to go in and find the side length, I'd take 2 times 6 minus 6. 2 times 6 is 12. Minus 6 is 6. So the length of this side would be 6. So now if I go back, let's take a look at the ratio between these sides. To get from 6 to 18, I times by 3. To get from 8 to 24, I times by 3. So this triangle right here is bigger, is a dilation of this triangle with a scale factor of 3. Okay, let's do this one real quick. So I'll set this one up. I'm not going to finish solving this one. I'll let you solve this one on your own. So this is like I have these triangles representing the distance across like a pond here. You see that? Where this side and this side are going to correspond, and this side and this side are going to correspond. So I have this bigger triangle and then this smaller triangle. So going off of the bigger triangle first, I could write x over 120 equals 135 over 90. X, this side divided by this side, is going to be equal to this side divided by this side. And I could cross multiply and solve for x. I will leave that one for you to be able to solve. So, coming back to this Thales of Miletus, the guy in Egypt with the pyramids, when two objects cast a shadow at the same time of day, those shadows do form similar triangles. So the shadow, you see this dude, he's 5 feet tall, standing up, his shadow on the ground is going to be proportional to this tree shadow. So, here there's a couple ways I can think about this. So I know that those two shadows that are formed, those two situations, are going to form two similar triangles. So I can write 5 over x, height of the dude, divided by the height of the tree, 5 divided by x, equals 7 over 14, equals the length of his shadow divided by the length of the tree shadow. So 5 over x equals 7 over 14. Well, if I cross multiply, I get 5 times 14, which is 70, I believe. 70 equals 7x. Then I'm going to go ahead and divide by 7, which gives me x equals 10. So the height of this tree is 10 feet. So I do want you to notice something right here from the get-go. We noticed that the tree's shadow was twice as long as the man's shadow. So in similar triangles, if this shadow is twice as long as the man's shadow, then the tree is going to be twice as tall as the man. So right off the bat, without even setting up this equation, I knew that the tree had to be twice as tall as the man. So twice of 5, double 5, is 10 feet. So the tree is going to be 10 feet tall. One of those cool things you can do with similar triangles. Okay, last problem I want to show you. This is a problem that I kind of actually did. So anybody, if you're familiar with Old Main, up at USU campus in Logan, Utah, Old Main is one of these really old buildings on campus. It's the one with this A up on top. So at a certain time of day, Old Main casts a shadow to the north that is 100 feet from the base of the front doors. So I have let me recreate this. I have Old Main, right? Here's the A. And it casts a shadow to the north that is 100 feet from the front doors. So this shadow right here is 100 feet. And my good friend Devin, so I have this friend Devin, he's who helped me with this experiment. He's standing nearby at the same time of day. And his shadow, he's 5 foot 6 inches tall, so he's like 5.5 feet tall. And he casts a shadow that's 9 feet long. So with this information, could I figure out how tall Old Main is? Yes, I could. I don't need to actually go out there with a tape measure and measure Old Main. I could use this to figure out how tall Old Main is. So that's what I'm trying to find, is how tall Old Main is. So x divided by 5.5, the height of Old Main divided by the height of Devin, is equal to 100 divided by 9. Old Main's shadow divided by Devin's shadow. When I cross multiply, I get 9x equals, I think that's 550. 100 times 5.5 is 550. And then I would divide by 9, which gives me an answer of 61.1-ish feet. If you go look it up, that's pretty darn close to how tall Old Main actually is, about 61 feet. So that's this lesson, guys. I hope that you are able to use properties of similar triangles to solve for missing sides of similar triangles. Use those properties to solve some real-world problems, especially like those ones with the shadows. Be able to find a scale factor for triangle similarity problems. How much bigger are these different triangles compared to their originals? So kind of rolling in all those things with dilations and similar triangles that we've talked about to solve these kinds of problems. So I hope that was helpful. I hope that was informative. Please let me know if you have any questions. Don't hesitate to reach out to me and to let me know. But I hope that was helpful, and I hope that you enjoyed it as much as I did.